Okay, this lesson is about 6.5, average value of a function. So let's start off by talking about the general idea of what that means. The average value, something which is an average. Typically you take something, you add up all the numbers, and then you divide by how many there are. Well, it doesn't really change. We're talking about the average value of a function. The average value, which is the y value of a function. That means the y value. So um, the general idea here is, if you think about what the integral actually meant, then what you were doing was taking an infinite number of rectangles between some curve and the x-axis, or between two curves, and you would add them all up, and that would give you the area between the curve and the function. That would give you the integral. If you want to find the actual average value of that function that you're taking the integral of, then you would just simply take the entire amount of rectangles and divide by how many rectangles there are. Well, the problem is you can't divide by an infinite amount, or at least not by the concept of infinity. So we'll come up with a slightly different way of doing this. Well, this is what is called the mean value theorem of integrals. If f is continuous, if it's a continuous function on the closed interval from a to b, then there exists a number c in that closed interval such that the integral from a to b of f of x dx, so just your basic integral of a function, equals b minus a times f of c. And that is what is called the mean value theorem for integrals. I'm not sure why this isn't working here. I'm trying to get a smaller thickness of this pen. Let's see. Yeah, that's better. Okay. All right, so what does this whole thing right here actually mean? Well, if you think about it, it actually means that you have just one integral. All right, I'm sorry. I apologize. Kind of getting a little distracted there. If you hear dogs barking in the background, I apologize. Sometimes my dogs start barking and I can't control that. Um, anyway, so what does this mean? It means that instead of taking the integral and adding up an infinite number of rectangles, what this really means is you're only going to need one, come on, draw for me, there we go, one rectangle to find the area, not an infinite number of them. And you might think, well, how does that work? How can that be? I'll show you. I'll try and illustrate it. But if you think about it, remember that the height of the rectangle is the function. So that's going to be our f of c in this case. And again, the c value is just, it's an x value, which locates the height of the function. And then the width of the rectangle is b minus a. So if you're having kind of a slightly more difficult time figuring out what that actually means, let me see if I can illustrate that for you. So what it says, that is a horrible line. Let's get rid of that. Let's try this again. Slightly better. So let's say we have this function, whatever this is, and we'll call this a. It doesn't have to be at 0, but in this case it looks like it might be. And then we'll call this b right here. If we have this function right here, what this is saying is if I took and put rectangles from here down, here down, here down. Here, let me see if I can actually draw that. It's not the easiest thing to do here, but I'm going to try. So if we drew like a rectangle here, another rectangle here, another rectangle here, and no matter what rule you use, maybe it's a left-hand rule or right-hand rule, it doesn't matter. If you draw and added up an infinite number of these rectangles, you would get some kind of an area here. Well, what this says is that someplace in here, between A and B, I'm going to find an x value that corresponds to a certain y value, which is your f of c on this thing, such that if I were to find that c value, and I drew the rectangle from here all the way over to here, and then I found the area of that rectangle, which of course is the height, which is f of c, times the base, which is b minus a. It's this distance minus this one. That's the base here. This area of this rectangle is exactly the same as the area of that curve. Okay, and these conditions will be met as long as f is continuous on a closed interval. Then there's going to exist this c value, which is this thing right here, this c value right here, which is going to give us the average height of the entire function. In other words, that one rectangle right here would give us exactly the same area as this right here. All right, so let's go ahead and take a look at what that actually means with some examples. Or we're going to try to anyway. Here we go. There we go. So this f of c that we found is called the average value. Average value. It's the average value on the interval from A to B. It's the average height of the rectangle that approximates the area. So again, here's our formula that I put on the other page. So all I did was I took this stuff and put it on the left-hand side, took the integral and put it on the right-hand side. Nothing wrong there. But what I'm going to do is typically we want to find that average height. We want to find that f of c. So to do that, we would divide the whole thing by b minus a, or more commonly, it would be written this way. Now, if you really think about what all this stuff means, the integral itself is saying, I'm going to take and I'm going to add up a whole bunch of things. And then by dividing by b minus a, that's dividing by how many things you have. So this literally is an average. I've added up a whole bunch of rectangles, and I'm going to divide by the total number of rectangles that I can fit between b and a. And because it's an infinite amount, it is just the distance from b to a. I'm sorry, from a to b. And here's our general formula. This is what it looks like. A lot of people just memorize this, but again, if you really think about what it means, if you're finding the average value of a function, if you add up all the values here of that function, which is all the heights of the rectangles, and then you divide by how many rectangles there are, you have the average value. Okay, pretty easy thing to actually put into concept, or to put into action here. Find the average value of f of x equals x squared on 0 to 3. And then we want to find where does that average value occur. So according to our formula, f of c, which is our average value, is going to equal 1 over b minus a. Well, this is a and this is b. These are your endpoints. This is your closed interval. So it's 1 over 3 minus 0, integral from a to b, so 0 to 3, of our function x squared dx. And then this is a relatively simple integral to do. So it's 1/3. Antiderivative here is 1/3 x cubed from 0 to 3. Multiplying the coefficients together, we get a 9th. X cubed, evaluated at 3 is 27. Evaluated at 0 is 0. So ultimately I get 1/9 of 27, which is 3. So what this says is the average value, or the average height, of x squared between 0 and 3 is 3. That's the average height of your function. And then it says, here this is part A, where does this occur? Well, if I want to know where this happens, I just basically need to figure out, okay, if this is the y value, f of x is y, so I'm going to set x squared equal to 3. And we're going to solve this thing for x. This is going to give us our c value. So x here would be taking the square root of both sides, positive and negative 3. But of course our domain here is only listed from, I'm sorry, that's not right. It's from positive and negative square root of 3. So the domain, of course, again, like I said, is 0 to 3, so the positive square root of 3 is the only thing in that domain, so the c value, there we go, is just the square root of 3. So what that really means is um, at x equals the square root of 3, the y value of this thing is 3, and that is the approximate one rectangle that you would need to make that would give you the same exact value as the integral from 0 to 3 of x squared. All right, let's go ahead and look at the next page. So one of the things that comes up with these types of problems is a tabular type of a problem. It just means that there's tables involved. In a problem like this, which is not extremely realistic, but we're going to use it anyway, it says a company introduces a new product, and the product, I should say in thousands of dollars, not I thousands of dollars, typo there, over the first 6 months is approximated by the model. So this is the model. The P, the profit, is 5 times the square root of t plus 30 in parentheses for times t equals 1, 2, 3, 4, 5, and 6. And we want to use this model to complete the table and then use the entries to calculate the average profit over the first 6 months. All right, so the idea is if we plug t equals 1 in here, square root of 1 is 1, plus 30 is 31, times 5 is 155. Now if you plug in 2, obviously the square root of 2 is some kind of a decimal approximation. So I've calculated these things. You can go ahead and plug them into your calculators if you would like to, just to see if you get the same values. But this is approximately 157, come on, point, why is it not drawing anything? 157.07. Since we're talking about money, we'll just go 2 decimals there. If you plug in 3 in for t, you'd get 158.66. Plugging in 4 actually works out to be a nice whole number because square root of 4 works. That's 160. Having a hard time drawing my ones there. Plugging in 5 gives you 161.02, no, 03 rounded, I believe. And then 6 is 162.25, I believe. So those are your average, that's your profit for the first 6 months. So if you just took these 6 numbers, added them up, and divided by 6, which would give you the average, it would be 159.03 or so for your profit. And that's really how you would average the first 6 months there. But I want to show you that if we want to find the average using the integrals, it's actually very close approximation to that. And it depends on what the function is as to what you would get. But one of the main differences here, we need to integrate from 0.5 to 6.5. Notice that the difference between these two numbers, a and b, is still 6. But basically, that's like taking the mid-month approximation, because if we started at 0 and went up to 6, we're actually starting at the 0th month right here, and that doesn't work. You could technically go 1 to 7 if you wanted to consider this one here as the end of the 6 months. We'll just call it the middle of the 6th month, or the first and second, or whatever. So we'll go 0.5 to 6.5. So our f of c is going to be 1 over 6.5 minus 0.5 integral from 0.5 to 6.5. There we go. Of our function, which was 5 root t plus 30 dt. All right, and while you certainly could go ahead and do this one by hand, we can go ahead and plug this thing into a calculator. So go ahead and plug that in. Clean that up a little bit there. It should be a 5. Um, and that way you get some practice on it. And remember, just use X's for T's. It's the same thing when you go to plug this stuff in. Make sure your syntax is right with your parentheses in the right spots. And you should end up with approximately 100, oops, mistake. You should end up with approximately 159.01. And that is pretty close. I mean, it's 2 cents off. That's a pretty darn close approximation for the average value. Now, if this was an actual function with a continuous, a continuous function listed for it, this would be the actual average value. That would be your f of c. Whereas this right here, because it's a discrete list of values and then we divide it by 6, is a very close approximation. However, in this case, if you're actually taking the mid-month approximations for your profit and then dividing by 6, this actually is your average. So it's really the difference between real-life data and a function which models real-life data. All right, let's move on to the next page. This is really moving slowly. I apologize. Just trying to keep the video relatively short, and my computer is just lagging really far behind right now. Excuse me. Okay, so I know you guys wouldn't wouldn't know the difference here, but I literally just sat here for about 4 minutes waiting for this thing to flip to the next page. All right, so here we are. Find the average value of f of x equals 2x plus 6x squared over the interval from 1 to 4. So this is some kind of a parabola. We just want to find the average value f of c between 1 and 4. So f of c is 1 over b minus a, 4 minus 1 in this case, integral from 1 to 4 of 2x plus 6x squared dx. So this is 1/3. Integrate. That's going to give us, let's see, raise the power, divide by that x squared. So that's x cubed dividing by 3, so 2x cubed from 1 to 4. So we get 1/3. Plugging in a 4, I get 16 plus, let's see, 4 cubed is 64 times 2 is 128. Minus, let's see, plugging in 1, I get 1 plus 2, so that's 3. So it looks like I get 1/3 of 16 plus 128 is 144, minus 3 is 141. Okay, that number is divisible by 3 if you didn't already know the trick. If you take the digits of a number and add them up, and that number, which is 6 here, is divisible by 3, the whole thing is divisible by 3. So a little bit of long division. 3 goes into 14 4 times, the remainder of 2, meaning that I've got 21 left over. 3 goes into 21 7 times. So the average value here, f of c, is 47. Moving on to example 4. Find the average value of cosine of x from 0 to pi. So f of c is 1 over pi minus 0, integral 0 to pi of our function, which is cosine x dx. So we get 1 over pi. Antiderivative of cosine is sine of x from 0 to pi. And if you plug pi in for sine of x, you get 0. If you plug 0 into sine of x, you get 0. So really, this whole thing is 1 over pi times 0, or just 0. So the average value of cosine of x from 0 to pi is 0. And that really should make sense if you think about what the function looks like. If you think about cosine from 0 to pi, this area right here is exactly the same as this area right here. So they cancel each other out, meaning that your average value is actually 0. It does make sense if you think about it. So yes, you can have an average value which is 0. You can have an average value which is negative. Number 5 here is very similar to our first example in the first page. Here we're doing f of x equals x squared, but this time we're going to go from 1 to 4. So f of c is 1 over 4 minus 1, integral from 1 to 4 of x squared dx. So we get a third. Integral here is 1/3 x cubed from 1 to 4. So I get 1/9. Plugging in the 4, I get 64. Plugging in the 1, I get 1, which is 63. 1/9 of 63 is 7. But here it's asking us to find the value of c that makes this true. So I need to take 7, which is my average y value, and plug it in for f of x and set it equal to this. So I get x squared equals 7. X then equals the plus or minus square root of 7, but of course our domain is only from 1 to 4, so it only involves the positive. So our c value is the positive square root of 7. That's what the question was asking. Alright, there's a lot of other pages to this. We are not going to go through all of them, but I kind of wanted to show you at least one of these things. So again, the AP test, which is for mostly high school, uses tabular things a lot. They give you charts and tables and things like that. We are not going to go through all of these different parts. Part A says use the midpoint Riemann sum. That's a Calc 1 topic, but you could do that using this chart as well. Based on the table, you could do acceleration, okay, all this other stuff. What it comes down to is right here at the, right here at the bottom, it's asking for, according to the model given in part C, which I'll go back up here and show you here in a second, what is the average velocity of the plane in miles per minute over the time interval from 0 to 40? So according to this, this was the velocity of the plane. If I want to find the average velocity of the plane, that's just an average value, so it's 1 over b minus a. This is b, this is a. Integral from 0 to 40 of f of t dt. This is f of t. You don't necessarily need to write out the entire thing, but when you go to plug this in your calculator, because believe me, this is a calculator type problem, you would type the whole thing in. Again, just be very careful of how you would do it. And what you would get is the average value comes out to be about 5.92 miles per minute. Would be the average velocity. And then if you have to transform that into feet or meters per second or meters per minute or whatever, then you'll have to do some conversions. But this is what they're asking for in this particular problem, is the miles per minute. We're not going to do anything on the next page, which is another AP problem example, and that's it. Okay, so there you go. That is our average value. Again, not too totally challenging. It's relatively easy to use. If they expect you to do something by hand, know how to do it by hand, but a lot of the times you're going to be able to do this in a calculator because the functions are not going to be very nice. All right, there you go.